Welcome to my talk on event-driven microservices. And really the goal of the talk is just to show how two architectural patterns, event sourcing and command query responsibility segregation, are a great way to build microservices. So in the course of the talk, I'm going to explain what event sourcing are and what CQRS is. Bit about me. So I actually got my start programming way back in the late 80s, building Lisp systems, compilers, runtimes, garbage collectors, Lisp, of course, being one of those very early functional and then object-oriented languages. And then eventually I ended up programming in Java, and back in 2006, my book Pojo's in Action, which was all about how to build apps with Spring and Hibernate, came out. And then a little later on, I started tinkering with this obscure service known as Amazon's Elastic Compute Cloud. That was back in 2007, and I think most of us have heard about that now, but that was the early days, and I got so excited by that that ended up creating a startup, Cloud Foundry, which was acquired by SpringSource shortly before SpringSource was acquired by VMware, and so that was back in 2009. Now, these days, working on a startup in the microservices space and doing consulting around modern application sort of development practices, NoSQL, microservices, and the like. And I've also created this website, microservices.io, which is a collection of resources to help get you started in the world of microservices. And here's a bunch more links, and there's some example code on GitHub in a repository, as well as my blog and then my Twitter. And then, so here's the agenda. So the goal is sort of like, why build event-driven microservices? Why should we use that as an architectural approach? Then I'm going to talk about event sourcing and how you design microservices using event sourcing, and then finish up by talking about CQRS, which is a way of implementing queries in an event-sourced application. So let's get going. So imagine that you're building an app. If you're like me, you typically would build an app that looked like this, where you've got a presentation layer. Say, this is a banking app. So you'd have a presentation, a UI that's, say, generating HTML. You'd have various back-end services to deal with things like accounts and customers and transactions and so on. So you sort of have this sort of nice modular architecture, and probably, perhaps you're developing it with Spring, MVC, and Hibernate, JPA, and that kind of thing. And then when it sort of comes to deploying it, you typically package it up inside a WAR file and run it on Tomcat, or if your boss makes you, you'd use WebSphere and package it up inside an IR file. And then on the back end, you'd have a relational database, and of course in the front, you'd sort of be serving up HTML to a browser. And for the most part, this is a nice, simple way of building apps, right? Our tools are good for building this style of app, and they're simple to develop, test, and deploy. We've got relational database that's got ACID transactions, so that's a nice sort of abstraction. We know that we make changes, they're going to be applied atomically and so on. And then if we want to scale, we can just run multiple copies behind a load balancer. And I think for most of the time I've built enterprise Java apps, I've built apps that pretty much look like this, and I'm guessing that many of you have as well. But where it gets interesting is that over time, apps have a habit of growing larger and larger, right? You have a team of developers who are busy adding lines of code, and you do that for 10 plus years, you're likely to end up with some massive application, right? Sort of this huge monolithic app. And that generally leads to a whole host of problems, right? So number one, you have a large app, it tends to be very intimidating to developers. It's just very hard to understand how it works, how to find your way around. It tends to be an obstacle to continuous deployment. These days, the state of the art is to deploy many times a day into production. And if you've got this massive monolith, that's really, really difficult to do. A large application tends to overload your IDE. I actually got this from Josh Long. developer advocate at SpringSource. And the funny thing is, it's like the horse is out in front and not overloaded by the sumo wrestler. But in general, right, the larger the app, the slower your IDE is going to be, and also the slower the container. I used to think that it was bad enough that apps, Tomcat could take 3 minutes to start up. But over the past few years, I've discovered that many folks have apps that take up to 40 minutes to initialize, and massive, complex app. And then a large application tends to be an obstacle to really kind of scaling development. You want to have functional teams where you have the UI team focused on the UI, the accounts team focused on accounts, and they want to be able to develop and deploy their changes into production somewhat independently, right? Trouble is, if at the end of the day everything's going into a monolith, that requires a lot of communication and coordination between the teams, right? The UI team might want to deploy their changes, but they can't because it's one of the back-end teams that has broken the build. And then lastly, large monolithic app tends to be an obstacle to, or tends to tie you to the technology choices that you made at the start of the project, right? It's very difficult to adopt new languages and adopt new technologies if doing so would require a major rewrite of the app, which is simply not feasible. So there's a whole host of problems with having a monolithic architecture. And then there's a whole bunch of problems with a relational database. On the one hand, that relational databases have served us well, but with modern apps today, you sort of run into issues around scalability or the need to operate a database across multiple data centers, or applying schema updates, which can be very time-consuming in a relational database. And then dealing with the traditional problem of mapping a complex domain model onto a flat relational schema. That's sort of still somewhat of a, just an inherent mismatch between the two. And then also relational databases don't deal with unstructured data very well. They just want things in nice sort of rows and columns and with a fixed number of attributes. So there's sort of a mismatch between the kinds of apps that we need to build today in terms of scalability and data models and a relational database. So what can we do about it? So in this book, The Art of Scalability, there's this three-dimensional model of scalability, the Scale Cube, which is a fascinating book, and a second edition is coming out, by the way. So there's two things that we can do to scale our apps. So number one is we can apply y-axis scaling or functional decomposition and split our apps up by function, but also functionally decompose the database. And then we can also apply z-axis scaling or sharding at the database layer. So, when we do that to our app, our monolithic app turns into a microservices architecture where each sort of distinct functional area of our app is now a standalone service with its own database. So we've sort of broken it up. And then we can also functionally decompose and shard our relational databases as well. So that sort of helps with the scalability thing. And then we can also use NoSQL databases. So if we need to do text search, rather than trying to do that in a relational database, we'd use Elasticsearch. If we're storing graph data, we could use a graph database for Neo4j, such as Neo4j. And these tend to be sort of databases that are designed to solve sort of specific problems in a more optimal way than a general purpose relational database. So we end up with an architecture that's quite different, and we end up with sort of a polyglot persistence architecture where each module can use a database that's best suited to store the kinds of data and to support the kinds of queries that it needs to support, right? So in our modern, so we've gone from a monolith using a relational database to a microservice architecture using a variety of different NoSQL and also possibly SQL databases. And that, on the one hand, that's good, right? It sort of facilitates agility and adoption of new technology and so on. But it actually ends up resulting in a whole bunch of distributed database management problems because we've chopped up our database and it has gone from a monolith into a whole sort of numerous smaller databases. And then if those smaller databases are using NoSQL, they don't have ACID transactions, right? So, as an example of that, imagine that you've decided to use Elasticsearch in your app. But then there's a problem, right? When I update my relational database that's storing my product data, how do I update Elasticsearch to keep it synchronized? So there's an example of a problem. Or if I'm using a NoSQL database and I need to update two entities or two documents, say in the case of a Mongo database, how do I do that without actually being able to have real transactions in that system? Or in Cassandra, where it's common to have manually maintain index tables, how do I keep that up to date with the main table, right? We can't do that in a transactionally consistent fashion. Or even back in the world of relational databases, if I functionally decompose the database and sharded it, then I could actually have accounts in two separate databases, money transfer objects in a third database. And so how do I actually maintain consistency across them without using two-phase commit, which is generally sort of not the done thing anymore. So in sort of our modern architectures, we've got a whole bunch of problems to do with the result from chopping up our databases and using NoSQL as well. And the solution to that is actually to use an event-based architecture. And the big idea here is that when one service changes some data in its database, it publishes an event, and then other interested parties, other components can consume that event and update their data to reflect the changes made in the first database. So as we've sort of gone from like two-phase commit to this eventually consistent event-driven approach. So if we go back to the example of Elasticsearch, when we update a product or create a product, we insert a row into MySQL and publish an event to a message broker saying product's been created. And then the search service can consume that event and then populate Elasticsearch with a document containing that product info so that it can then be queried for a text search. And then if we're doing the same thing with the money transfer thing, we can actually accomplish that by using this event-driven workflow. So we create a money transfer that publishes an event which gets consumed by the account service, which can then debit an event. I'm tripping over a cable here, which can debit the account, which then generates its own event, which then gets consumed by the money transfer service, which records that, and then publishes an event to say, I've recorded the debit, which gets consumed by the account service, and sort of so on. So these events sort of ping-pong back and forth between these services, and after an exchange of like 4 or 5 events, the money transfer has been performed. So that's kind of the basics of an event-driven architecture. But actually, in order to do that, that introduces yet another problem. How do we atomically publish an event when a domain object changes, right? Because that sort of translates into how do we atomically update the data store and publish an event. So, one way of doing that is to use two-phase commit, right? So both the message broker and the data store participate in a distributed transaction. But that's sort of that works, but that's kind of the technology we want to avoid using, right? And it also assumes that both the database and the message broker support two-phase commit, which is not true anymore with a lot of popular technologies. So that's not a solution. And then another option is actually to use the data store as a message queue. So eBay have actually done this to keep multiple relational databases synchronized. So basically the way that works is you have a transaction that updates some record, and then within that transaction you queue an event in an event table, which functions as a message queue to say, I need to do something somewhere else in the system. And then there's another transaction that actually consumes that event and updates the target database, and then there's a third transaction that marks that event has been consumed. And so that sort of worked well for eBay. There's a fascinating paper about that. But that kind of only works with relational databases, and there's a bunch of code that you end up having to write. Kind of intertwines event publishing and business logic all in the same module. So and it only works with NoSQL. So that's a problem. So that's, so it's like on the one hand, we've gone from a monolith to multi-database microservice architecture, and then within that, we have an event-driven architecture, but then we've got this problem to solve. And that's really the big motivation behind using event sourcing. It turns out that it's a great way to just tackle all of these distributed data management challenges. So what is event sourcing? So the big idea is that for each of the aggregates, sort of the main business concepts like order, account, shopping cart, etc. in your application, you actually identify state-changing events, so events that sort of have meaning in a business context. So for an account, that would be account opened, account credited, account debited, etc. And you actually define event classes, so we're explicitly modeling the events that occur at a business level in our application code. So that in itself is not that big a deal. But where it gets interesting is that rather than persisting the current state of a business entity, so for an account, the standard thing, of course, to do would be to have an account table with a balance column. We don't do that. And instead what we do is persist the sequence of state-changing events for each entity. So for an account, there would be a sequence that began with account opened with a particular balance, and then you'd see a series of credits and debits. And we never store the current state. Instead, what we do is when we need the current state, we actually query the database, retrieve all of those events, and replay them to reconstitute the current state. So, in a bank account, that would be taking the initial balance from the account opened event and then summing up the debits, adjusting it by the sequence of debits and credits. So it's a very different way of actually persisting events or persisting the state of an entity. And the reason that's really interesting in this scenario is whereas before we had to update state and publish events, with the event sourcing model, instead what we do is simply persist events. And they implicitly get published. So we go from two things that have to be made atomic, which is kind of tricky, to basically one thing, persisting events, that just is inherently an atomic action. And so it sort of solves all of these problems of solves the problem of simultaneously updating and publishing by kind of wrapping it up into one. And then in the system, the way the requests get handled looks something like this, right? So a request comes in, a controller would ultimately call code that it needs to update an entity. So it goes and retrieves that entity's events from the database, instantiates a new entity using its default constructor, and then applies those events to actually reconstruct the current state. And I'm going to show an example where you have an object, a domain class that has an apply event method that just updates its state. And then we process the command, which comes from the request, and that actually yields new events. And then those events get persisted in the event store. So that's kind of the flow for request processing in this application. And then where it gets interesting is, see, the event store is acting both as a data store of events and a message broker, because other services can then subscribe to those events, and then when those events get persisted, the interested consumers get notified so the event gets published, and they in turn can then go and update other entities in the system, which triggers more events to get published. So you can kind of imagine sort of a cascade of events being triggered. Or they can update some materialized view, such as Elasticsearch. And I'm going to dive into both of these in a bit more detail. But that's the big idea behind event sourcing is, so you're persisting events inside an event store instead of persisting current state. And then other parties can actually subscribe to those events, and then they get notified when events are persisted. And there's various implementations out there, like lots of folks actually just build their own. I've talked to various people who have built event-driven systems without actually calling them event source systems. And then there's also Get Event Store, which was created by Greg Young. And that's sort of off in the .NET land, but Greg Young's kind of been pioneering event sourcing in CQRS for a number of years. And I'm actually working on an event store as well, and love to talk to people about that. And then, of course, you might be wondering, well, you know, if you have a bank account that's been open for a very long time, that's a large number of transactions that have to get loaded from the database. And the solution in the event sourcing world is actually to periodically take snapshots of the current state, so that when you need to reconstruct the current state, you find the latest snapshot and then load the events that have occurred after that snapshot and then reconstruct the current state. So you don't actually have to always go back to the beginning of time and retrieve all of the events. And that tends to work quite well. So let's have a look at some code. Hopefully you can read this. There's actually sort of, in the examples I have on GitHub, there's a couple of different styles. And there's actually a Java version of this as well, though in the talk I'm just showing two different styles of Scala code. And so one of them is kind of a more traditional sort of inheritance-based model. So there's an interface aggregate, or a trait in Scala that implements an apply event method. So that's the state changing method. So you invoke apply event on an entity, and that actually passing in an event, and that actually gives you back an updated entity. So it's using immutable entities here. And then there's a command processing aggregate that extends aggregate and adds a process command method. And process command takes a command and returns a sequence of events. So those are the two fundamental operations. Take a command, give me the state-changing event, and then apply each event to return the updated state. And here's actually the code for an account. So it's process command methods using a Scala pattern matching, which is basically a giant switch statement. So it just says if it's open account command with an initial balance of that, return the account opened event. Credit account command returns an account credited event. And then there's two cases for trying to debit the account. One is the overdrawn case. One is the success case where the amount that you're trying to debit it by is less than or equal to the balance. And then the other case is if you're trying to do a debit that would make the account overdrawn. And if any of you work for a bank, I apologize, because I really do not understand how banking works. So this is my naive domain model.
This is actually almost exactly what they do.
Yeah? Awesome. Yeah, you know, it's funny. I've been using a money transfer example, like even in my book from 8 years ago, and it's like I still do not really know what a banking domain model looks like. But anyway, so this is my 2015 version. So you can see how process command takes commands, turns them into events. And then the apply event actually takes an entity and an event and gives you back an updated entity. And so it's, once again, it's doing pattern matching, and you can see that like account debited event takes the amount and then uses the case class copy method to create a new account where the balance has been debited, and then the account credited method version does something a little similar, but it's giving you a new account where the account has been credited. So it's kind of cool with Scala with case classes, because you can just copy these immutable objects, modifying them using the copy method. So that's kind of what entities look like. I mean, it's a very different style from this usual update in place, but if you actually look in the GitHub, the Java version is sort of a more traditional approach. And here's the API for the event store. So there's sort of like save, update, find methods. And then I also have a more functional example, which is using Scala, or basically like Scala type classes or implicits. So whereas in the old version, the previous version, the count had to implement an interface, which on the one hand is not bad. It's sort of not very kind of Pojo, right? You're kind of coupling yourself to some other framework. With these basically function as strategies. So you can see here's another version of well, this is a money transfer. So you got the money transfer class that's just pure data. And then there's this object that implements aggregate that provides the behavior. And so it's sort of a more functional approach, and money transfer is passed in as a method argument as opposed to being, this. And so it's sort of two different styles, and you can pick the one that you prefer. And event store has similar methods, but the signatures are all slightly different. So that's kind of what domain objects look like, and it's sort of like, well, why should I do this? What are the benefits of event sourcing? And so, number one, event sourcing gives you a built-in audit log, right? Whenever you change the state of an entity, that results in an event, and the events get saved, and you can always go and look at the events to see what happened and when and by whom. And you're guaranteed that it's going to be 100% accurate, whereas if the traditional approach of like bolting on auditing logic after the fact is sort of a very unreliable way of implementing auditing, because if you forget to add the right auditing calls in your code, then you're going to miss something, right? And then another really interesting thing is because we're saving all of the events, we can actually go back in time and ask what the state of an entity is, right? Which in some domains is extremely useful. So you kind of got the temporal query concept. And then once again, that's quite difficult to bolt on to a traditional current state-based application. And also the other thing, modern apps usually kind of have some machine learning component that's driven by user behavior. So if you've implemented business logic in a way that's generating a stream of events which represent what users have been doing, those events can be fed into a predictive analytics engine to personalize behavior. And then you're also preserving history of everything that's happened in the system, which in some situations means that you could actually today implement new functionality, but kind of process all of that historical data, and the net result is it's as if you implemented this new piece of functionality sometime in the past, which is quite powerful. And then there's a whole, the technical benefits. Number one, it actually solves all these data consistency problems that, I kind of talked about in the introduction, right? For maintaining consistency across multiple databases. And then for the most part, it actually solves or at least simplifies the whole OR mapping problem, because we're persisting events, not mapping our domain objects to the database. And in many cases, the events actually have a very simple structure, so they're very easily persisted. Where there are some domains where that's not true, but in a lot of cases, you can just simply serialize the events as JSON or some other format quite trivially. So there are, of course, some drawbacks, right? For using this approach. Like number one, it's like weird and unfamiliar. It's a very different, this event-driven approach is a very different and unusual style of writing code, and we're just sort of not used to of writing code in this style. So it takes a little bit of getting used to. Another potential problem is, these events live forever. Yeah. Whereas if you make a mistake with your database schema, you can always migrate the schema to kind of fix up the problem, right? Whereas the events are just these immutable things that in theory have to be around forever, and you can't go back and fix them if you've done something wrong. Though in practice, that might be less of a problem, because usually the events are very much grounded in the problem domain. And as a result, they tend to, they're sort of well-defined business concepts as opposed to inventions of developers, right? So they're sort of, they're much more likely to be well understood and well defined by the business rather than being sort of artifacts of the solution. Yeah, well, yeah. There is that. But you could say, like in banking, right? Ledgers have been around for a while, right? A few centuries. Whereas sort of the stuff that we as developers make up, right, it's, kind of less well-defined. Now, of course, there's sort of, another issue you have to deal with is this is a message-driven system, and so there's the whole issue of like handling duplicate events. But in practice, you can just kind of keep track of the last event you processed, and assuming events have monotonically increasing event IDs, you can then detect duplicates quite easily. And then also there's this, I'm going to talk more about this in a minute. Applications end up having to handle eventually consistent data. So they might make a change and then query some other data store that's updated by consuming those events, and there might be a sort of replication lag, so to speak. And then the other issue is the event store itself only directly supports primary key lookup of events by entity ID. And so when you need to use joins, say more complex queries, you actually have to use what's known as CQRS, which I'm going to talk about in just a minute. All right, so so how do you use all this? Well, so imagine you've been told to go off and implement microservices with event sourcing, and there's really kind of two different levels of design that you kind of have to do. So number one is the strategic design, where you need to identify your microservices. And then there's sort of the more tactical design, where you're actually designing the model inside each microservice. So if we look at sort of strategic design, I think there's a lot of useful sort of guidance from domain-driven design that can help with taking a problem domain and turning it into microservices, right? So imagine, you've got some nebulous domain and it's banking. So step number one is really to identify all the various subdomains, or sort of the functional areas of the business. So like for dealing with customers, for dealing with accounts, for dealing with transactions. And then you can turn those into bounded context, right? And to use domain-driven design speak, which basically transform into the microservices themselves. So we kind of end up defining microservices for each functional area of our business. And I think that's sort of like a good first pass at doing this. Though, of course, you need to iterate on this a few times. And then you actually need to decide what the communication mechanisms are between all these different services, right? Because service X might need data from service Y, so it's sort of just kind of consuming data. And then that could be implemented by X making an RPC type call, REST or whatever. Or maybe Y is publishing events and X is consuming them and maintaining its own denormalized or materialized view of data that's owned by Y. Or conversely, maybe X needs to tell Y to update itself. And that can't really be done in RPC because we're not using two-phase commit. And that's where event sourcing really comes in, right? So, if a change happens in X that requires a corresponding change in Y, then Y would just consume the events coming out of X and then update itself accordingly. So that's, sort of a high-level kind of design thing. And then, if you're working on, you've got some million-line monolith that you want to break up, right? Into microservices. So one strategy is to implement new functionality as a standalone service. So we've got our big, horrible monolith, but then we've got a nice, pristine service. And then we write this anti-corruption layer, to use some more DDD terminology, to kind of make the two work together. Or you might identify some existing code inside your monolith that you then want to move out and make that a service with a corresponding glue layer to tie the two together. So it's sort of like you got greenfield development, then you've got the scenario of refactoring a monolith. And so the net result is you've kind of identified services. And then within each service, there's sort of the tactical design layer, which is kind of where you're using the familiar domain-driven design building blocks of like entities and value objects and repositories and services and so on. But then kind of what you want to do is like take your domain model and really identify the aggregates, sort of identify the little clusters of objects that form the key business entities like order or account or customer. And then for each one of those, identify those state-changing events, and then and then explicitly model them as classes, right? And there's a few things to think about, like, well, the name. Well, the name tends, events are something that have occurred, so, right, your name has to reflect that. And they would have attributes like the ID, which could be like a time UUID, so every event gets time-stamped with when it happens. And then they have other attributes which tend to be from the command. And then there's sort of an issue around, like, do they have a minimal amount of data that's just there to support kind of updating the aggregate, or do you add extra data? Do you enrich the event to add extra data that is needed by the consumer of the event? So the example of that is when you add an item to a shopping cart, you publish an item added event, and you just include in the event the item ID, or do you actually have some extra data like the item's name and so on that can be that's useful to the downstream consumers of the event? And so there's some issues there around kind of deciding how rich your events should be. So then once you've done that, you can think of, well, what does my microservice then look like? Well, it tends, it's going to have an aggregate or multiple aggregates within it. And then there are various adapters that handle requests coming in from the outside world, HTTP requests or messages coming in from like a enterprise-y messaging bus. Those events are then turned into commands which get processed by the aggregate. And then the aggregate then persists events in the database. And then there's also an adapter that's actually consuming events from the event store and turning those into commands. So commands are being generated from the outside world, but also from events that are happening within the system. So in terms of code, here's an example of a Spring MVC controller that's handling a post request to create a money transfer. And it's actually using the deferred result async mechanism in Spring MVC, and at the same time the code's written using Scala futures as well. So there's kind of a translation from Scala futures to Spring MVC deferred results. But it basically asynchronously calls the money transfer service and creates a response object. And then the money transfer service has this transfer money method that takes the details, and then it's written using this really kind of simple little domain-specific language that kind of encapsulates the mechanism for interacting with the event store. So it actually says, create a new entity of type money transfer and have it process this command. And under the covers, it's actually creating the aggregate, processing the command, applying the events, and then persisting the events in the event store. But you never actually have to use those lower-level APIs. And then the other part of it is handling events that are published by accounts. So there's a handler, event handler for an account debited event that's also implemented using a DSL. So it's saying, go find the existing money transfer entity whose ID is that, and then have it process the record debit command. And then under the covers, it's actually loading that aggregate, loading its events, reconstructing it by replaying those events, processing the command, applying those new events, and then also persisting the events in the event store. But that's sort of the kind of code that you end up writing in this model. And I found that in the app I've worked on, it's worked quite well. But there's sort of this big problem, right? So the whole event, as I mentioned earlier, the event store only supports primary key lookup of events. But typically, if we're to get the data that's displayed by a page, you end up having to effectively do a join. So imagine you want to display an account and the recent transactions. So that's like a join between an account and all of the money. That's like an outer join between the account and the money transfer transactions that have transferred money into that account or out of that account. And so we can't do that with the event store in any sort of meaningful way. And that's where the second pattern comes in, command query responsibility segregation. And what that really means is that rather than a component in our system handling both commands, in other words, the updates, and the queries, as the name suggests, we actually split them apart, and we end up with two different systems. The command side, which is basically everything I've talked about up until this point, and then we have this query side. The command side handles the updates, the query side handles the queries. And they're just two different modules in the system now. So the command side handles updates, so effectively the posts and the puts in HTTP sent, and updates aggregates, publishes events, and then the query side subscribes to those events and maintains a materialized view of the world that can then be queried. So in terms of microservices, it looks like this. So you have some kind of view store that's sort of appropriate for the kinds of queries that you need to support. So it could be Mongo, for example, or if you needed to support graph queries, it could be Neo4j, or if you need to have text queries, it could be Elasticsearch, or in the app I've built, I use Cloud Search. And then you have a service that's consuming the events coming in from the event store and updating the view store. So if it's interacting with a text search engine, it's creating docs or updating docs and having them re-indexed. And then there's the query service that's handling the HTTP GET request and then querying the event store. So we're no longer sort of burdening the command side with supporting this. And so in the example code that I've written, I've got a MongoDB-based service that's subscribing to all of the account events and the money transfer events, and actually for each account maintaining a document within MongoDB that's storing the most recent transfers and the most recent debits and credits for each account. And then here's the service, so it's got a bunch of event handling methods that are subscribing to the events. So that's how we can, in an event source system, support queries by actually moving the query handling into an entirely separate module. And so in the stuff I've worked on, I've used Cloud Search, which is Amazon's hosted text search engine. And then I've also used DynamoDB, Amazon's hosted NoSQL service as well. And that's actually worked quite well. So that's kind of the whole big idea of CQRS. You actually split apart the system. So you have a command side that's using the event store, and then you have a query side that's consuming the events that are coming out of the event store and updating these materialized views. And that sort of kind of has a bunch of benefits, like it's simpler because you're doing this separation. You can actually, kind of in theory, each part has become simpler. If you actually go back and look at your domain objects, in practice you find that a lot of the attributes they have are really, you're sort of combining responsibilities in a given domain object. Like some of the attributes are there for handling updates, whereas other attributes are actually just for handling the views. And so now we're separating them apart, so we end up with two simpler things. And then also this approach supports multiple sort of denormalized views of your data. So you could have a view that's maintained in Mongo, right, for supporting like denormalized by key lookups. And then you could have another view that's maintained inside Neo4j for doing graph-related queries. And so you kind of have optimal query implementations, which would be quite difficult to do if you had to just do it all within one data store. So you can get much better performance and scalability and so on. Drawbacks, of course, is like, well, complexity, right? I mean, there's some potential for code duplication between the two. And then also, there's sort of the standard risk of kind of basically like replication lag, right? Where you could actually do an update that goes to the command side, and then you turn around and query the query side for the entity that you've just updated, and the change is not propagated yet. And so in some systems that can be a problem, but like, one common solution is in the UI, you just update the UI with the assumption that the change was made, and with the knowledge that by the time the user ever kind of navigates away and never navigates back, the database will have been up to date, will have been updated at that point. So in theory there's a problem, but in practice it tends to be much less. So anyway, that's I think pretty much my talk, right? So kind of in summary, event sourcing is this great way to address these distributed data management challenges that you get in NoSQL and also microservice applications. And then, you can use DDD to sort of design your system and design your aggregates. And then CQRS is the way that you actually handle views within such a system. So that's kind of the talk, and I hope that you found it useful. And please follow me on Twitter, check out my blog, and send me email, etc. So thanks. And yes.
So I'm making an assumption.
Oh.
Recorded for posterity. Okay. I'm making the assumption that the event store in any non-trivially large system is not just a monolithic event store, correct?
Yes, correct.
So then my question is, can you provide some guidance on how to pull apart what in your head is one big event store?
Well,
how do you break that up?
Oh yeah, I mean, that's an interesting issue. So if you think about how you access the event store, it purely is by primary key, right? So that's an inherently shardable solution, right? So you could actually, in terms of the event store, it could be this replicated service, and you just use the hash of the primary key, or use the primary key to decide which one of those replicated instances to query. Right, so it's a very partitionable problem.
But then the structure is the same for every piece. Sorry. So the structure is the same for every piece of the event store then?
Yeah, that's sort of the other interesting thing, right? So in a traditional app, we have to think carefully about schema design, right? So there's the account table, the transactions table, and so on, whereas effectively in an event store, there is simply the events table. And so you never, you know, it's just a standard table. If you actually did it on top of a relational database, there would just be basically one table in your system. And regardless of how many different types of entities are in your domain models. And yeah, reluctantly, Toby will ask a question.
Because you know I got the question and you can't answer. Where do the IDs come from? How do you? Where do you get these primary keys?
Yeah, that's actually a very good question. Like I'm actually using what I think you would call time-based UUIDs.
Because the problem is that my web browser.
Please repeat.
Who creates them, right? So the problem
yeah.
is that my web browser goes to place a money transfer order, right, and then needs some kind of reference to that object to then go query
okay.
it.
Yeah, so that's an interesting one. So, so the way I've implemented it right now, so when you create an entity in the data store, you do a post, and the ID generation happens server side, right? And then the response comes back and tells the client what the ID of the newly created entity is. So it's kind of like MySQL generated kind of ID mechanism basically. But in theory, I mean, you could actually, I mean, if the clients had a UUID mechanism, they could be responsible for doing that. But right now, it's kind of server side.
Hi, I had a question. So the problem I see with this design is that you're turning the event store into a critical piece of your infrastructure. If that thing goes down, nothing works anymore, right? And the second follow-up question on that is, who is responsible for ordering the events? Is it the event store or is it something else?
Oh, okay, yeah. So yes, the event store it's a critical piece of the infrastructure, just in the same way that a message broker is or a database is.
If the event store goes down, that means you cannot create new events, right? So you can not process new commands, but you may still read whatever was there before. So you get, by separating them out, you get the implicit, read-only failover mode, even if the event store just totally blows up.
That's awesome, yes.
Plus, one of the other things that I've seen happen as well with the model for event sourcing, especially when you combine it with microservices, is the idea that you could just have the event store specific to the microservice so that you're isolating it even more and so that you don't end up with just another monolith to replace the other monolith.
S/could/should/.
Good. I'm going to let you guys answer because those are brilliant answers. And then actually you had a second part to the...
Ordering the events.
Oh, okay, ordering the events. So the events just sort of... they're ordered in just the term, basically in the order, effectively, that the client is posting requests, create an update request to the server, and so at that point they're like assigned event IDs and then published. And so the actual, in terms of what the ordering guarantees that are made, it's more like if you're looking at events from a given entity, you will see them in order. Whereas events coming from different entities, the ordering is, ordering is only defined in terms of what's coming from a given entity.
When the section where you split the query side over from the command side, from the data modeling standpoint, one of the questions and concerns I have is that you're violating the dry principle in terms of your system of record, and you're relying on this
Yeah. I mean, I guess if you wanted to, you could run some kind of consistency checker periodically to just make sure that stuff gets dropped. I mean, I would like to think that you can make the sort of the event store as incredibly reliable, so that's quite unlikely. I mean, if you wanted to, what's interesting is you could actually, this is sort of kind of ties into the Lambda architecture, right, and big data, where you could actually reconstruct a view from scratch by just processing all events from the beginning of time and just repopulating the view. I mean, which, you know, obviously there's efficiency issues around that, but that's kind of like the Lambda approach, right? It's just to periodically rebuild those views from scratch using, quote, big data technology, right? Yeah. I mean, so that is a possibility if you're concerned about lag, but I you know, like my goal would say the event store is to just make it reliable. I guess we're good. Thank you.